So the video you have just seen is basically a class project of machine learning course which is made by the students of Millennium Institute of Technology, MiTE, under my supervision. In this class project, it's a relatively small project because it was only for to make them understand how machine learning algorithms work. They have used two machine learning models. One is called Whisper, which is to convert audio to text, and the other one is SVM. What this project is actually doing is that we have got, as you can see in this video, that we have got three boxes in front of this xArm robot of Hiwonder, and according to the command given to it, for example, in this one video we had given the command to pick the green box. So this robotic arm picked the green box from these three boxes and placed it over here, as you can see in this video. And for that we have used Python code, and we have used Arduino. You can see this, the controller over here. This is the Arduino controller. So here on this laptop we have got the Python code which processes the audio and gives command to this Arduino over here in the Arduino controller. Arduino controller forwards this instruction to this controller, servo controller of this xArm robot. So I will show you how all this works together. First I will explain you how the Python code works, then I will explain you how this Arduino code works and how it passes the calls the action group of this xArm robot. So first I will explain you how these programs interact with each other, and then I will explain you the codes line by line. This is the Python code, and function of this Python code is that when we give the voice command, that voice command is converted to text using Whisper, and then the word, for example, pick the box, red, green or blue. So we will try to get that specific word from that voice command. For example, we have to find if the user called for red box, to pick the red box or green box or blue box. So if that color is mentioned in that sentence, then we have to pick that word, and accordingly then this program will find the position of that box using the image processing. And for image processing we have used OpenCV and SVM. Once the position of the box is detected, then this program will send the instruction to the Arduino program. What it will send? It will send whether to pick, the command will be either it is 1, 2 or 3. These 1, 2 or 3 are according to the position of the box. As you have seen in the video that we have got 3 positions of the boxes. So for each position we have a separate sequence of actions used in xArm robot. So what we have to do is that we have to call that specific routine of actions in the xArm. So this instruction will be sent to the Arduino. Arduino will send it to the xArm controller, and then that routine will be executed. So as you can see that from Python we will get the command into this Arduino code, and here this myController.run action group will send the appropriate routine. So we start with the Python code. So first of all we have to train the model. Here we are using SVM model, and for training here we have used the RGB colors values. So in xtrain, in the first row, we have got all the RGB values for red color, and they have been labeled accordingly. For example, this 255,0,0 is labeled as red. This 200,30,30 is also labeled as red, and so on. So these color values have been labeled, and of course they are the values, true values of these colors, which we will use to train the SVM model. Why have used the values instead of images of the boxes? Because this is a class project, so students didn't have enough time to train the CNN model, get the boxes, pictures, images, and then train them. So to keep it simple, we have used these color values. Now then we have to encode it. For that we have used label encoder, because as we know that these strings cannot be used in training. So we need to encode them. So first we call this label encoder class, and then we call le.fit transform method of that class to convert it into encoded values. So here we have got ytrain encoded. So if we are going to encode these values only, these labels, and what kind of labels we will have. For example, for red we will have 2, for green 1, or something like that. So this encoded value will be used in the SVM model at the time of training. Next we have used min-max scaler. What's the purpose of min-max scaler? It is a tool from scikit-learn. It scales or normalizes your numerical data so that each feature value falls within a specific range, typically 0 to 1. Why do we need to scale it within 0 to 1? Because SVM requires it. SVM requires these RGB values in the range from 0 to 1. So for that, what we have done is that we have scaled these color values from 0 to 1. First we created this string values, then we labeled them using ytrain, then we encoded them, these labels, and now we are scaling these xtrain values between 0 to 1. So for that we use min-max scaler, and method which is used is scaler.fit transform. Xtrain scaled will have values of these colors between 0 to 1. Then we have called svm.cvs. Support vector classification, SVC, a type of support vector machine. This SVC is a type of support vector machine with a linear kernel, which is used for binary or multi-class classification problems. So for multi-class or classification problems we use SVC, and linear means you are assuming your data can be separated by a straight line. As we have seen that we use either use linear function, or we may use polynomial function, but for because here we are using simple 3 boxes, square boxes, which are easily differentiable, so here we can use linear function. Then we trained the model here, clf.fit xtrain scaled, ytrain encoded. This line is training the SVM model, and as you can see that we have used xtrain scaled and ytrain encoded. Now we have got the trained model of SVM. Next we have to take the command from the user, and we have to convert it into text to understand what the command user has given. So the whispered speech model is an automatic speech recognition system developed by OpenAI that can convert spoken audio into text, also called speech to text. Whisper is an automatic speech recognition system, and it converts the speech or spoken audio into text. Whisper is a deep learning model trained on 680,000 hours of multilingual and multitask audio data. The Whisper uses a transformer-based deep learning architecture similar in design to model like GPT, but tailored for speech processing. Here we have used sample rate is equal to 16,000 samples per second, and duration is 5 seconds. Duration of speech is 5 seconds. And then we have trained the model using Medium. So this is a pre-trained model where you can use different models, small, medium, large. For our purpose, this Medium model is good enough. So we have used Medium model. Audio data is equal to sd.record int sample rate into duration, comma sample rate is equal to sample rate, channel is equal to 1, and d type is equal to np.float32. Now we understand each one of them. This is the core audio recording line using the sound device library SD. This sd.record will start the recording of audio. First we will record the audio. Int sample rate into duration is the total number of samples to record. How many samples will be recorded and what will be the duration? That we have determined using sample rate and duration. So for example, if I make this duration 1 second, then how many samples I will have? 16,000. If duration is 2 seconds, then I will have samples 32,000, and so on. Why 5 seconds? Because it is assumed in this exercise that 5 seconds are good enough to give the command like pick the box or get the red box or pick the blue box. So this time period is good enough. But if a user finds it not enough, then the duration can be increased. So example, sample rate is equal to 16,000 and duration is equal to 5. It records 80,000 samples. Simply multiply 16,000 by 5. Channels is equal to 1 means record in mono, and d type is equal to np comma float32, record the audio as 32-bit float values. This is required by ML models. Most of the ML models is a standard format for many ML models. NP is numpy, which we have seen over here. Numpy as NP. Now after recording, we have to wait for recording to complete. Why? Waits until the recording is finished before continuing. Without this, the program may try to use the audio before it is fully captured. So if we will not use this sd.wait, then it is possible that the audio is not fully captured and we move to the next command. So this will make sure that it stays there. This recording is done for 5 seconds, and then we will use the flatten function to change the shape of the data, this audio data. So flatten converts it into N shape needed by Whisper. So this is the requirement of Whisper, because we will send this to Whisper, because Whisper has to understand convert this audio to the text. Next function is recognize command. So first creates a temporary .wav file on disk using Python's temp file module. This is temp file.name temporary file. We will use it to create a temporary file, and its suffix is .wav, means we are giving it .wav extension, and delete is equal to false keeps the file after closing it. Important for Whisper, which needs a real file. And f is a file object you can write to. Next, we are going to convert it into np.int16. Whisper expects 16-bit PCM audio. but sound device gives float 32 audio in the range of minus 1.2 to 1.2. So this line converts it into integer 16, signed 16-bit integers using standard audio scaling. So because we are going to pass this data, this audio data to Whisper, so Whisper expects it to be in 16-bit PCM or audio, so that's why we have converted it to integer 16-bit. scipy.io.wavefile.write writes the converted audio to the .wav file using scipy.io.wavefile.write, and fnim is the path to the temporary file. So this is only just for the to save the file in the .wav extension or format. Next we have to use f.flush. It makes sure all the data is physically written to disk before passing the file to Whisper. Without flushing, the file may be incomplete when Whisper tries to read it. Next we have result is equal to model.transcribe. Model.transcribe converts audio to text. This is here we are converting the audio to text. We have already trained the model. Here model is equal to whisper.load load model medium, and now we are doing the conversion and saving the result in result variable. So model.transcribe converts audio to text. Transcribe returns a dictionary containing text, segments and language. So it will return three values: text, the transcribed speech itself, segments, if it's too long then it will be divided into segments, and the language it has detected, whether it is English or any other language. And then we just get text out of it. We leave segments and language, we just get text out of it and we convert it to lower. Now we have another function called find box position, because we have recorded the audio and we have converted it to the text, and from text we have to find what instruction was given or command was given by the user, whether it asked to pick the red box or green box, and we have to find the position of that box accordingly. So for that we use camera, as you have seen in the video. So first we have to start the webcam. So cv2.video capture opens your default webcam. Of course, if your default webcam is not your external webcam, if it is your built-in laptop webcam, then you will have to disable it to use it. Otherwise, it will always go on your default webcam, which is built in the laptop or your some other device. So here we have, it is possible that if this webcam is being used by some other application, then it will not open. So first we check if cap is opened, means that some other program or application is using the device, then it can give you error, cannot access camera. For underscore in range 30 cap dot read, this for loop reads 30 frames to allow the camera to auto adjust brightness focus. So this loop is only will keep reading the getting the input from the webcam for 30 seconds, 30 frames, and it will give the time for camera to adjust its brightness and focus. Next we use get mask. Now these functions are used to apply image processing on the images which we are getting from the camera before we pass it to SVM model. This will improve the object recognition And this pre-processing is very helpful in correct image detection. This is not part of your machine learning process. Actually, this is only to make the image more clear. So arguments are HSV, lower and upper, and returns what? CV2 in range, HSV np.array lower, comma np.array upper. So this line checks each pixel of the HSV image. If a pixel's color is between the lower and upper bounds, it returns white 255 in the mask. If not, it is black 0. For example, lower and upper for red color are 0, 100, 100 and 10, 255, 255. The mask will return all red pixels white and everything else black. So this masking will help us to detect the object. It will separate the image from its background objects. Obviously, if there are, for example, if I want to detect the red box and there are other objects in the background having red color, then this object detection will become difficult. So we have to take care of that. Then in the background we should avoid red, green and blue objects. So what it will do, for example, when I will use this get mask function, it will give me all the pixels having red colors as 255 white, and all the other pixels values in surrounding this red box will be 0. Now we apply morphology on this mask. What is morphology and why do we apply this on mask? This function cleans up the mask by removing noise and making the shape of the detected object clearer. So we are actually removing the noise. And what is noise? For example, there is some other object in the vicinity which is also red, some small dot of red or something like that, which is not actually part of the red box, or otherwise maybe due to some lighting or some shade there is white pixels which is not considered as red on the box. So we will remove those values as well. So first we will use a filter or kernel. Size 5, 5 creates a 5 by 5 square matrix filled with ones. This matrix is used as a structuring element for morphological operation. Mask is equal to CV2.erode. So erosion makes white regions shrink. It removes small white noise, false positives, good for removing tiny dots or thin lines in the mask. And similarly, we will dilate also. Dilation makes white regions grow. After erosion, some desired areas may shrink too much, so dilation restores them. Applying it twice helps ensure full shapes are recovered. So all these morphological methods will help to make the object more clearer and remove the noise, means unwanted or false detection of 0 or 255. So it will return mask, means image which we have detected without noise. Now we have to find color of the box. We will pass this object mask, from which is returned by this apply morphology, to this function. Here you can see it is mask. Then we have got label, image and box colors. So contours comma dash is equal to cv2 dot find contours. So it finds the outer lines of white shapes in the binary mask. cv2 return external gets only the outer contours. It is possible that this object may have internal boundaries as well, or because of shading it may have multiple boundaries within the object. So to make sure that it returns only the outer boundary, we use this return external. And this chain approx simple compress the contour points to save memory. So it is not really required for this processing, it is only to save memory. For CNT in contours, now goes through each detected contour in the mask and measures the size, which is in actually pixels, of the contour. So means we have to determine what is the size of the box in terms of pixels. CV2 dot approx poly dp we use. What is it, approx poly dp? It stands for approximate polygonal curve using the Douglas-Peucer algorithm. This algorithm takes a curve made up of many points, returns a simplified version of the curve using fewer points, and keeps the shape similar but with fewer vertices. So here we are using approximating the contour points, and basically we are simplifying the curve points. CV2.approx poly dp is an OpenCV function that approximates the shape of a contour, reducing the number of points while still preserving its general form. If it is a rectangle or a square, approx will have 4 corners. Then we have CV2.arc-length, which is used here. CV2.arc-length. What is it? CV2.arc-length calculates the parameter length of the contour CNT. True means the contour is closed. For example, if the contour is a square of side 100, the parameter is equal to 400. And that parameter 400 will be multiplied by 0.04. What does it mean? 0.04 means a maximum error of 4% of the parameter. Now we are going to use this reduced size of contour and check if the image is a box. So if approx is equal to 4, why it should be 4? As I mentioned over here, that if it is a rectangle or a square, approx will have 4 corners. So its length should be 4 in that case. And area is greater than 500. Why we have used this check? Because if it the area is not too small, because this is to avoid very small rectangles or objects maybe in the background or in the surrounding of the box. To eliminate those small boxes, we have used minimum area, which should be greater than 500. We get the values of those edges or contours in x, y, w and h. This line computes a straight rectangle that completely covers the contour CNT. For example, CV2.bounding rect returns a rectangle like this. X will be 100, y is equal to 50, w is equal to 60 or h is equal to 60. Depends on what is the size of the box. Which means the rectangle starts at position 100, 50 and it is 60 pixels wide and 60 pixels tall. So this one x, y gives the starting point, a starting position, and this gives you width and height. So if it is both are 60, it means it's a square. And if the width and height are different, then it means it is a rectangle. This is useful to draw boxes around detected objects. If you will run this program, we can see that the green box or green rectangle will be drawn around the surrounding the detected object, and above that we will see the label of that color. Calculate center positions, check shape ratios and pass position to hardware like Arduino robots. Next, if we will see if it is square or not. So if width divided by height is between 0.8 and 1.2, so they are nearly equal. And why we have not just used the exact one, why we are giving the range? Because when we will detect the box, then it is quite possible that it is not exactly square. So ensure we only accept box like shapes, not long rectangles. Means we want to detect only the squares or boxes. Then Cx is equal to x plus w divided by 2 finds the center x coordinate of the box. Here this double slash means that the division will be rounded to the lower side. Means, for example, if the result of the division is 2.5, then it will be rounded to 2. Box colors dot append cx dot label. So saves the horizontal position and label, whatever the label of that color is, it will be saved in box colors. And this rectangle will be drawn around the box, as I have told you, and put text will put the label on that box. Cap.read grabs a frame image from the camera. Ret is a boolean, true if frame was successfully read. Frame is the actual image. So in frame we have got the image, and this RET we are getting the boolean value whether the image has been captured or not, image is read or not. If not read, continue, means if the image is not detected, then it should not move further and it should go back to while over here. Now we resize the captured image to 640 by 480 and save it in IMG, and then we convert the image from BGRG color to HSV. We are going to work on HSV, hue, saturation and value, and HSV is more effective for color detection. First of all, we have to define the upper bound and lower bound for each color. Why? Because if we look here in get mask function, here we have got this lower and upper boundaries. So of course we need to define these lower and upper boundaries for each color as well. So all the colors within that lower and upper will be converted to white, and rest will be converted to black. For green, lower and upper are defined, and for blue, upper and lower are defined, but for red we have defined 2 upper and 2 lower. This is something important. Why is that so? Because red is split into 2 ranges due to hue wrapping. In OpenCV's HSV, hue ranges from 0 to 179 and not 0 to 360 like standard HSV. Red is special because it lies at the edges of the hue spectrum. Hue wrapping means that hue values wrap around a circular color wheel. So hue 0 to 7 and hue 0 and hue 179 both represent red. So we have this defined it. Lower is 0 from 0 to 10 and 160 to 179, and then we use the get mask function. Here we have passed the HSV, this one, this image which we have captured, and these boundaries mask. So of course what will happen, what we will get over here in this red mask 1, red mask 2 and green mask, we will get an image having all zeros where we have found this boundary, for example according to green one, and rest will be black. Now find color boxes. In find color boxes, this is the function which we have created here, find color boxes, and for that we have used 4 parameters: mask, label, image, box colors. Red mask, this is the image which we have got over here, and then we have labeled it as red. This is IMG image which we had here, this one. This is the processed image, this is the actual image, this is the label, and this is box colors. So finds boxes of specific color, labels them, appends their x coordinates and color to box colors. Next we have to sort the box colors, and for that we have used key is equal to lambda b colon b and index b index 0. This is a little bit different because it is used only Python, so let me explain it to you. Sort by x coordinate so that leftmost box is first. So we are sorting the boxes and their indexes from the left to right. So left one will be 1, then next to it will be 2, and the next to it will be 3 or 0 1 2, like that. Box color is a list of tuples like cx comma label, where cx is the x coordinate of the center of the box and label is red, green or blue. Here lambda b colon b index 0 is an anonymous function that takes a tuple b and returns the first element of the tuple. Lambda is used to create anonymous function, a small one-line function without a name. It is like a shortcut to define functions where a full def block would be too long or unnecessary. Here, this lambda is an anonymous function where it will return first element of the tuple, which is cx. So it will give me the coordinates or the cx value, and it will sort it accordingly. So the lowest cx value will be the first one, then higher will be the second one, then higher than that will be the third one. Next is detected colors. Box colors list has tuples of coordinates center and color. So this is a concise way to build a new list from an existing iterable, in this case box colors. From box colors we are going to create a new list. In this list, dash means is a conversion in Python to say I don't care about this variable. So the first variable will be ignored in the box colors, and the color name, this is what we want. So it will just give me the colors. This this box color has got both the coordinates and colors, but I want to get colors out of it only. If detected colors is not equal to last detected is equal to detected colors. Means if I have detected a new color, then my new color will become the last detected color. If set detected colors is greater than equal to red, green, blue, what does it mean? This checks if all three colors are present in the detected color list. Since we have to determine the position of these boxes, we need to detect all the three boxes first. So it is possible that not all the three boxes are detected simultaneously. Maybe just one is detected and the rest of the two are not detected, or two are detected and third one is not detected. But we don't want to proceed with just one is detected or two is detected. We want to detect all the three boxes and then we want to move on. So because we have to determine the position of the boxes according to their x coordinate values. So if all detected start is none, on first detection all three colors, it stores the current time. All detected start is equal to time.time. Initially in this program I had used this time, but it is not required anymore, so this can be skipped as well, but I have not skipped because I had to change this if else so many things, so I have just left it. But anyhow, this time is not used in this program anymore. For I, color in enumerate detected colors. For each color in detected colors, sort left to right, find the index I of the target color. So we have to find the index of the target color, whether for example if blue is on the leftmost, then the index of the blue will be 0, then index of red will be 1, and index of green will be 2. So that will be returned, but before returning it we will add 1 in it, because to Arduino we have to send 1, 2 and 3 instead of 0, 1, 2. So we just add 1 in this index. Index 0 will become 1, index 2 will be index 1 will become 2, and then we have created a window to show the boxes in case if boxes are not properly detected. So you can see what's happening in this window. This displays the current frame in a window titled color box detection. The image has already been processed to show rectangles and labels around detected boxes. This is where I told you that you can see the green rectangles around the boxes and labels on top of them. This window refreshes in real time every time a new frame is processed. So you don't need to refresh it, it is refreshed automatically. Now once we have got the index of the box, then we have to send it to the Arduino. For that, first of all, we create the communication with the Arduino, and for that we use serial, where we have defined port and the baud rate and timeout is equal to 3, and then write SAR write object ID dot encode. So by using this command, we will send the command to Arduino. We will see how it is used when we will call this function. Now we come to the main function, audio array is equal to record audio. This is the first function which we have created here, record audio. So first of all, we have recorded the audio in main record audio function. Then command text is equal to recognize command. This is the next function which we have created above, where we pass this audio recorded audio array to it as parameter. We have to find whether that particular color was defined in that text or not. For example, in command text, we will search for this word red, this string red. If, for example, I have said pick the red box or get the red box, so of course when it will be converted to the text, the red, this string red will be there. So I am searching this red in this command text. If it is there, then what I will do, I will find box position which is red. For red, I will get what? It will return me, for example, red is in the first position, then it will return me object ID of it as 1. If I said green and object ID of green was 2, then I will get here 2 and accordingly here 3. This object ID will be sent to the Arduino. This object ID is used here, and as you can see here in this Arduino, if I will get 2 over here, then this 2 will be sent to the Arduino. SCR.write will send it to Arduino, and that's it. This is here this job of the this Python code is done. It has to detect the image. First of all, it has to take the user command, convert it to the text, then find the position of the image, and then send it to Arduino. Now we see how this Arduino code works. Here we have defined LEDs pin number 13, LEDs 13, RX pin is 8, and transmission pin is 9. So this receive pin 8 and transmission pin is 9. We use software real MySerial receive pin and transmission pin. So what this software serial does, so it creates a software based serial communication on a user defined pins, receive pin and transmission pin. Software serial allows communication on other digital pins besides the default hardware serial pins 0 and 1. So this software, using this software serial, you can use other pins, digital pins, instead of default hardware serial pins like pins 0 and 1. Next we have Lobot servo controller. It creates an instance microcontroller of the Lobot servo controller class. This object handles sending commands to and receiving data from the servo controller using MySerial port. As I told you that Arduino will send the command to the servo controller board of the xArm robot. So it will do the communication with the that servo controller board of the xArm robot. Next we have MySerial.begin 9600, means it starts communication with servo controller at baud rate of 9600, and serial.begin starts the default hardware serial connected to USB at 9600, means this one will communicate with the Python code your on your laptop or computer, and this one will communicate with the servo controller of the xArm. Pin mode LED output configures the LED pin as an output, and delay is 1500. Waits for 1.5 seconds, allowing time for the servo controller to power up or reset properly. And controller run action group sends command to servo controller to run group 0 once home to decide the position for all servos. When I will show you how this xArm work, you will know what this group 0 does, and this one is very obvious that this action group will be called only once. It will run only once. And then we have got delay of 1000, which means that wait another 1 second to ensure the reset action completes. Then we have my controller.receive handler. It processes any incoming data from the servo controller, keeps the communication link active up to date. If serial.available, checks if data has been received from the PC via USB. Int command is equal to serial.parseInt. Reads an integer value from the serial input like 1, 2, or 3. It waits until number is received or timed out. So this object ID from here, send command to Arduino, this object ID 1, 2, or 3, it will be sent to here, this one, int command is equal to serial.parseInt. Then it will just prompt you whether what has happened is it has received the command, and will print the command as well, whether it received 1 or 2 or 3. And if the command is between 1 and 3, it makes sure that command is between 1 and 3, then my controller.run action group will be executed, and it will tell which action group is to be executed. Since we have to execute 13, 14, or 15 according to the position of the box, so we have used 12 plus 1, means that 12 plus 1 13, 12 plus 2 is 14, and because we are going to get either 1, 2, or 3 from the Python code. Now how we see how this xArm works. Here you can see that we have got these values 500, 500, 500 for each servo motor. We have got 6 servo motors from ID1 to ID6. This 500 is its you may say default value. When we'll call this action group 0, it will have all these values to set to 500, means that here ID will be 500, it will also be 500, this will also be 500, all these values will be 500. So we will have our xArm something like this in this form. The formation of the initial formation of the xArm will be something like this. When I will call for action group 13, then we will have these values. For example, initial value of ID1 will become 300, ID2 will remain 500, ID3 this servo will become 300, and so on. So it will start moving according to this. So it will move from, for example, if you can see that here this ID2 value has changed from 500 to 430. So this servo ID2 will start working, and it will move this arm according to these values. But we have to actually execute these values. So what the action which you have seen in the video is executed by these values one by one. For example, the first one, this one will be executed, then this one, as you can see that these values have changed, then this one, then this one. So this is how this whole project works.